going to be quick as possible. So today I'm Yanchi from Rutgers University. Today I'm going to talk about unified point of interest recommendation with temporal interval assessment. This is the outline of my talk today. First, I'm going to introduce some background. So as we all know that location-based services are now very popular today, such as Facebook, Twitter, Yelp. They all provide some services to let users to share experience, opinions, or comments on a point of interest. For example, at the first picture here, when I arrived in the KDD at the first day, I checked into Hilton to share to my friends. I'm excited to be here to attend KDD 2016. And so one point of interest can be a restaurant, a hotel, or a museum. And there are billions of check-ins have been generated by millions of users. And there are even more check-ins are generated every day. So with tremendous point of interest there and check-ins, POI recommendation is an important service to help users to explore new POIs, since users kind of hard to choose from a large set of POIs. And there are various factors can influence the POI check-in. The first one is user interest preference, right? For different users, you can have different interests. And the second one is social influence. You tend to be influenced by your friends, right? And the third one is geographical preference. People tend to choose POI nearby other than the POIs far away, since travel also costs time and energy. And the first one is temporal preference. As we can see that for the different time of day, as in the morning or in the evening, you tend to go to different places for different activities. So, but consider one scenario. When you traveling in a city and after you have some activities, and you are wondering where you want to go for tonight and for tomorrow. I think you are expecting different places, right, for tonight and tomorrow. But the existing recommendation models cannot provide you a recommendation for the specific time period. So why time matters so much? As the goal of POI recommendation is to recommend the right POI to right user at the right time. So it's essentially one of the important factors in the POI recommendation. Since users' preferences gonna change over time, maybe you are interested in a restaurant in Chinese food today, and then you change to Thai food tomorrow. So people's preference gonna change over time. So we need to capture the different preferences to make the right recommendation. And also another important factor is that the timing for recommendation is also very important to make user easier to accept your recommendation, right? Although you can capture the right interest for the user, but you recommend in the wrong timing, I think the user not going to accept your recommendation, right? For example, if you plan to go to a museum, I think you want to take some time to learn some background of the museum to see if what kind of activities you can conduct there and what kind of exhibitions are there in the museum. So how to achieve our goal to make the right recommendation at the right time? So we need to learn the transition between different POIs, but not only the transition, but we also want to learn how the transition evolving with the time. that means we want to evaluate the distribution of the time intervals between POIs. But other than that, we also want to learn the user interests as well. So here comes our three main challenges. So first, we need to identify the checking patterns between the dependent POIs. We definitely do not want to recommend the future POI based on a non-relevant history, right? And also we need to consider these two different preferences together, how to unify them into one model. That's another challenge. And I want to mention that although we focus on these two preferences here, but we can consider other factors into our model that can be easily integrated. And the third one is how to learn the preference from sparse observations. Since for each user there are not many check-ins to let us to learn. So, and with the pair of the POIs, that can make the observation each even sparser. So this is a much difficult challenge than the existing POI models. So here comes our problem statement. So we have the user check-ins, and also we have the POI information. We want to recommend the POIs based on the probability of visiting for a specific time period, such as tomorrow or next week or tonight. And the core task is to learn user interests and the evolving sequential preference for each user with a collaborative way, right? We also need to borrow the community opinion from others to make the recommendations. So our proposed method is shown here. So with the user check-ins, we first need to extract the sequential patterns for each user. So for each user, we can extract a sequential pattern as a matrix of the transition between POIs. Then for all the users, we can form the matrix as a transition cube. From the cube, we want to model the interest preference and the sequential preference for each user. So that's the modeling of the preference. After that, we want to evaluate the parameters of our model with a node and graph construction. So after we get the estimation of the parameters of our preference, we can recommend POIs to our users based on the distributions. So the first step is how to extract the sequential patterns. Take a look at, here we have one example. This is a sequence of the user check-in. And to the POIs A, B, C, D, and we can form a matrix from one POI to another. So we can, for example, as a POI A to C, we have two transitions here. So we only choose the nearest ones and discard the far away ones. So we have two temporal interval here, which are two. So we have one item in the matrix as a sequence of the temporal interval. So we can form the matrix as the sequence of temporal intervals. And for the diagonal items, we can also extract the user interest from the items as the number of the as the occurrence of the check-ins, right? So in this way, we can unify the two different preferences into the same transition cube. And for each item in the transition matrix, we use a Gaussian distribution to model the sequential preference. So we kind of have a best timing from one POI to another, and the probability of your weighting between these two POIs is gonna have a distribution with the best timing. So, and this applies to our observation that we can find this the Gaussian distribution. But however, we want to model the sequential preference only based on the relevant POI pairs, right? As we mentioned before, we do not consider all the POI pairs as relevant. So we use a max operator here to identify the strongest temporal dependent POI between the pairs. So in this way, we can filter out the non-relevant POIs. So that's how we extract the sequential preference. And for the user interest preference, we use a Poisson distribution to model the user interest. As we can see from this figure here, the frequency of one user checking into different POIs follows Poisson distributions according to user interest. One user tends to check into several few POIs much frequent than others. So it's kind of follows a Poisson distribution, and we can have the observation of the checking frequency as the number of the visits to one POI, and for each user, for each POI, we have the number of the visits. So with these two preferences modeled by Gaussian distribution and Poisson distribution, we can transfer the sequential patterns as a bi-weighted graph. We use each node as the user interest and the edges between the nodes as the sequential preference. In this way, we represent it as a bi-weighted graph. And we want to estimate the parameters, which is mu and nu here. Mu is for the Gaussian distribution for each user, and the nu is for the Poisson distribution for each user. Right? And we want to estimate the parameters collaboratively. So we use a low-rank graph construction method to estimate the parameter. We assume that we have k graph bases, which has two parts. One is the beta as the Gaussian distribution basis, and the gamma has the Poisson distribution basis. And we want to reconstruct the graph from the k basis with a weight alpha for each user that's differently. So, and also we treat these three two bases and one weight vector as a latent variable, as shown in this graphic model. So we treat these three alpha, beta, and gamma as the latent variable, and we have a prior of the latent variables. For the Gaussian, we still use a Gaussian, and for the Poisson distribution, we use a gamma distribution as the prior. So in this way, we can formalize the graphical model. And in this model, with the observations, as the C is the visiting frequency of POI, and D is the sequence of the temporal interval between POI pairs. So we can estimate the latent variables, alpha, beta, and gamma from this graphical model. And we use an alternative algorithm to estimate the parameters. But for more details, we can discuss offline. So the objective function is to maximize the probability density of the observation by combining these two together. And we use the prior as the regulator to the objective functions. So after we estimate all the parameters of the distributions, we can make recommendations based on that. So instead of a single time step t in the previous distribution, we want to make recommendations for a time period, right? So from t to t plus delta, we can calculate the expected visiting frequency based on these two distributions by combining them together. So the first part is the user interest, and the second part is the sequential preference. And here comes our experimental result. Our experiments are conducted based on two data sets. One is Foursquare and the other is Gawana. And we want to make recommendations for a specific time period. So the Tn here is the current time, and the delta can be deemed as to specify the time period. And we want to say that if the small data is 0 and the uppercase delta can vary, and that means for different lengths of time period, how our recommendation model performs. And for a specific constant time period, maybe for 1 day, and how our recommendation model performs. We want to test from these two different perspectives. So we use the first 80% data as training, and the last 20% as testing. And we use 3 baselines: PMF, FPMC, and PIMF. And we use F-measure and NDCG as our evaluation matrix. So here comes our result. For the performance of recommendation, use the small data as 0 and the large data as 24. So that means for the next 24 hours, how our performs. So we can see that our model can achieve best performance with data from 12 hours to 1 week. So that means the reason why we have this best performance during this period, that's because most of the relevant POIs, their temporal interval are between around several days. So that's why we can capture this preference between the POI with this time period. And also, for another experiment, we want to test how our performance in every day. For example, here that's for the next week. For every day, how is the performance? We can see that our proposed method can outperform others, since the reason is that the other recommendation models do not specifically make recommendation for a specific time. Okay. And here comes our conclusion. So if we can capture the user interest and the sequential preference, that can help our recommended POI at right time. And our proposed low-rank construction method can learn the parameters from sparse observations effectively, and our experimental results show the effectiveness of our method. And thank you. Any questions?
And for the POI recommendation, your time interval is for the next 24 hours for your experiments. Have you tried for like 1 hour or 2 hours for the next POI recommendation?
Yeah. Also, we tried for different data here. So for 1 hour, I think our model is not the best compared to others. Only the FBMC can achieve better performance. I think since that one is trying to capture the next POI recommendation, so that's why they can capture in a short time. But for most of the POI transitions, they are between several days, so that's why our model can better capture that distribution.
Okay, thank you.
No problem.
Any last burning question? Okay, in that case, let's. Oh, one more.
Thank you for the great talk. So you assume the Gaussian distribution for the time intervals, so there can be negative time intervals. So how did you handle that?
Yeah, for that question, that's a good question. So we just treat them as positive ones, and when we estimate the observations, we make the estimation just as the positive ones. We do not use negative ones. That's all.
Okay, thank you.
Right, let's thank the speaker and congratulate all the authors of the papers in the session. Thank you.